In this presentation, I'm going to be going over phase diagrams, both what they are and how to use them. So basically, a phase diagram is a graph of pressures and temperatures that show us that what phase of matter exists at different combinations of those temperatures and pressures. Notice that temperature we put on the x-axis at the bottom here, and pressure we put on the y-axis on the side here. We can also see that solid materials usually exist on the left of these graphs under high pressures and low temperatures. Liquids exist at, you could say, middling temperatures and high pressures. And gases usually exist on the right side of the graph and the bottom at high temperatures and low pressures. And this pattern follows what we talked about in our previous set of notes. So let's talk about how to use these diagrams. Basically, what we do is we go to the x-axis for a certain temperature, the y-axis for a certain pressure, and we'll find what combination they give. On this slide, I'm going to give a quick example. This phase diagram shows water specifically. Basically, every phase diagram is specific to one material, and this is for water. Let's say we want to know what phase water, or H2O, is in when it's at 50 Celsius and a pressure of 10 atmospheres, or ATM. What we do is we'd first go to 50 Celsius here on the x-axis, not labeled in this diagram, but I can give us a 50 right here, between 40 and 60. We would then draw a line straight up from 50. We'd go to 10 atmospheres on the y-axis right here, and we draw a line straight across from 10. And where these intersect is right in the liquid phase. So water at 50 Celsius and 10 atms of pressure is a liquid. Now, when it comes to these lines on the graph, these show when you transition between phases. For instance, let's say we had a material that started at this temperature and pressure and was a solid. If we increase temperature to the point where we go into a different phase, we have transitioned from one phase to another. In fact, if we start here at a solid and we go straight across to a liquid, this would essentially show a melting transition. Now let's say we started at this temperature and pressure for a liquid, and we did the opposite. We lowered the temperature until we became a solid. This liquid turning into a solid, this would essentially show freezing. So when you cross these lines, direction does matter. Now, let's take a look at how this works. Let's say we have this material, and we know it's starting out at, we'll say, 70 atms of pressure and 200 Celsius. I'll actually find that right now. I'll go to 200 Celsius on the x-axis, 70 atms on the y-axis, and I can see that where these intersect is a solid. Now let's say we're going to increase the temperature to 500 Celsius right here. Does this material change phases? We're starting at the point and we're going to the right to 500 Celsius. We can see that we started as a solid, but we went to a liquid. So yes, this material does change phases. It in fact melts because it's going from solid to liquid. Remember that these different names for transitions, they're in your Unit 4, Section 1 notes. Now let's look at a slightly different scenario. We'll actually start in the same spot. We'll start with 70 atms of pressure and 200 Celsius. So if this material is at 200 Celsius and 70 atms, it's in the solid phase. But let's say we lower the pressure to 20 atmospheres, but we keep the temperature the same. I'll take my starting point and I'll go down to 20 atmospheres of pressure right here. This material went from solid to gas during this transition, so this does change phases. Now, solid to gas, we had a specific word for. According to our Unit 4, Section 1 notes, that is sublimation, when a solid goes directly to the gas phase without becoming a liquid first. And that is how we use phase change diagrams.